Current is just simply the rate of change of charges, that is dq by dt. In this particular case, how do we take the values of, or how do we represent current and voltage in numerical sense? In order to produce the same 100 joules of heat, how much power did I use? I naught is the peak value of current, hence I naught is nothing but the peak value of current is given by I naught. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we are going to start a new chapter here today that is known as alternating current. We studied about current, electricity, what is current, what is electricity, what is moving of charges, and how magnetic fields are affecting it. Now we are going to study about alternating current. So what does this alternating current actually means? So AC, also known as not air conditioning but alternating current. So what is this alternating current? For that, first we need to know what is current. We already learned what current is. Current is just simply the rate of change of charges, that is dq by dt. When charges actually move, we can call it as a current. So imagine that there is a lot of electrons like this, and if these electrons move through a wire, then we can say that, hey, there is current being produced. So this particular electrons get upon a scooter or a tricycle or something, and they just roll off like this because of some force being applied. That is usually a potential difference that is being applied. So because of this, the electrons will just zoom across this particular wire, and hence it is known as current flow. But there is one catch. When we apply a potential difference like this using a battery, and the electrons are moving in this particular direction, because here it is positive and here it is negative. Anyways, so if the electrons are moving like this, then this particular current is known as unidirectional current, or simply direct current, or simply DC current. So this current, also known as direct current, is the current we have been seeing throughout this particular discussions. So now we are going to see the elder brother of this particular current, that is AC current. So what exactly is the difference between AC and DC? Sir, current is current. It is both resulting from the flow of charges. More precisely, it is resulting from the flow of electrons. Hence, current is current. What is the difference between DC and AC? So the main difference that you feel from AC and DC is that the way that they actually behave itself. So for example, if I want to draw a circuit which is containing a DC current, I'll just do this. So there is a positive, a negative, and current. Since there is a potential difference, there will be a flow of charges, which means current will be flowing through that. Or simply we can say that electrons are moving through like this towards the other end. That is what is happening in this particular circuit. That is direct current or DC current. But what happens in AC current? That is the current that you are getting in each of your homes. So when you reach out and grab DC current, it is not that much dangerous. But any current that is about 25 milliamperes is enough to stop your heart. But again, comparatively, we say that generally DC current is harmless. You can touch out a battery, you can grab a battery like that, and nothing will happen to you. But if you do that with the AC current that is coming through the lines, that is entering into your homes, if you go ahead and grab the electric wire near a post or anything, you'll be immediately shocked, even dead, or even burnt, or even many damages can happen to you. So why is that happening? The difference is in the nature of these currents itself. AC current is more dangerous, that is true, and AC current is also much more efficient. So why is it efficient? Why is it dangerous? What is the difference? All this is what we are going to learn in this particular chapter. So let me complete the introduction. So again, here the electrons are moving steadily across this particular circuit. So hence, if I draw a graph, let's say if I draw the graph of DC current, I'll get it as a smooth straight line like this. This will be the nature of DC current. DC current will be flowing like this. If I take time like this, and if I take voltage in one axis, I can say that DC current will be flowing like this only. With respect to time, if I measure the current or voltage, doesn't matter. It will be unidirectional and it will be a straight line like this, which means there is very less variations and current will be flowing like this. The electrons are actually physically moving around like this in all the animations you have ever seen. In all the animations you have seen of current, you can see electrons moving in a straight line. That particular current is known as DC current. Now, what about AC current? That is alternating current. So, in an AC current, this is how we represent an AC current. For DC, we use a battery like this with a positive and negative end. For AC, we use a curve like this. It is to represent a wave. So, we use a wave inside a big circle and then we connect it to, let's say, a resistor like this again. And if I measure this particular current, the nature of the graph is utterly different. So if I measure the nature of the graph that is obtained from AC current and compare it to DC, it will be very different because the nature of the graph is like this. That is why the symbol is here of a wave. So this particular wave function, which resembles a sinusoidal wave, is actually very different from the DC current because it is having a positive part, it is having a negative half, and it is throughout changing. Here it is a constant value. If I measure voltage, okay, it is V only. But here if I measure, it is V1 here, it is V2 here, it is V3 here, and it starts to decrease. V4 is different, V5 is different. So everything is having different values. The current is actually instantaneously changing. But here, if I measure the current, it is not changing. If I measure the voltage, it is not changing drastically. But here, at every point in time I measure this particular current or voltage, it is ever changing. Which means that alternating current, which means that current that is alternating between positive and negative sides. So initially it was positive, then it was negative, then again it will be positive, then again it will be negative. So every second it is oscillating between positive and negative, positive and negative. It is alternating its state from positive, negative, It's changing its phases. Hence the name alternating current. Again, so why is this current dangerous? What is happening here? Why is the nature of this graph like this? That is all what we are going to study here. But one more important thing you should understand is that the electrons in this particular current, that is, if I take the same wire example again, and if I say electrons are here, here and here, in DC current we saw that they get on a cycle and they just swiftly move away. But for AC current, that is not the case. For AC current, these electrons do not actually physically move away. What they actually do is that they actually oscillate back and forth. Hence this particular graph. Hence the positive and negative sides. Hence the nature of this particular current. So when this particular AC current is applied, that is alternating current, what it actually does is that the electrons will actually jiggle. The electrons will actually, if this is the electron, it will actually jiggle here and here. It is for DC, it is like this, moving from left to right or right to left. But for AC current, it is going forward and coming back, going forward and coming back. It is actually oscillating back and forth. So that is what is producing this particular wave function. That is how actually AC current actually behaves. That is some of the things you have to actually understand. And one more thing, if we apply Ohm's law is applicable to DC and AC currents, no problem. But we apply Ohm's law to DC current, we'll get a simple value, that is V directly proportional to I, or we can simply say that V is equal to IR. We can apply Ohm's law directly because the current is not changing, the voltage is not changing. So we can directly apply that. But For AC current, we cannot do that because the value of voltage is continuously changing at each instant of time, which means that we cannot take the average value of this particular voltage. Again, the reason why we cannot even take the average value of this particular voltage is because here if we take the average value, there's no problem. It's a unidirectional current. The values is not changing that much. We can take care V or V bar, we can take the average value. It's fine. But here, we cannot take the average value over a set time because it is positive in one half and it is negative in the other half. So if we take the average, that is, if we take this side and add it with this side and divide it by the number of cycles, we'll get 0 because again, this is one positive half and one negative half, which means the average will be 0. So which means we cannot even take the average value. So what do? We actually have to take the instantaneous values of voltages and currents for an alternating current. That is, we have to take the instantaneous value of voltage or current in order to apply to any equations. So how does that actually work? So imagine that I have a resistor R connected to an AC power source. So this is an AC power source. So it provides AC current to that particular circuit. So if I graph out that particular current, if I graph out the values of voltage and the values of current, this will be the nature of voltage and current that is passing through that particular circuit when I use a resistor. So you can see that this blue line indicates the value of current that is passing through and the red line indicates the value of voltage. You can see voltage is a bit higher, current is a bit lower. Anyways, now in this particular case, how do we take the values of or how do we represent current and voltage in numerical sense, or how do we represent using mathematics? Because we need mathematical representations so that we can form equations and find out the mysteries this particular phenomena or this particular AC current holds. So again, it's not AC current, it is alternating current, AC itself, but habit of saying, I might say it, so please forgive me. So again, here we have two peak values. So this particular wave, which resembles a sinusoidal wave, which means a sine wave. So here you have a 0 point, that is a neutral point at the starting position, and you have a maximum point at pi by 2, that is 90 degrees, you have maximum point, and again at 2 pi you have a minimum point, which is all representing a sine wave. So sine wave also has a neutral point, that is 0 point, and then you have a maximum point at pi by 2. At 2 pi again you have a 0 point, and then at 3 pi by 2 you have a minimum point. At 3 pi by 2 you have the value -1, that is the minimum point. So it oscillates or it propagates like a sine wave. So since it is similar to a sine wave, we can actually use a sine wave to represent this particular current source. So again, how do we represent voltage and current in this particular case? So since the red line is indicating voltage, we can actually say that this particular wave will have a maximum peak position, that is the amplitude of that particular wave. Let's say this is the maximum peak position of that wave, that is the amplitude given by V naught. The maximum value of that particular wave, that is the height of that particular wave, maximum height is given by the value V naught, because this red line indicates voltage. So that maximum value is indicated by V naught. Now this blue line indicates current, which means the maximum value of that particular point is indicated by I naught. So just remember that current can be represented as a sinusoidal wave. There is a maximum peak position, that is the maximum amplitude for each of these waves, and that is indicated by V naught and I naught. So V naught indicates maximum displacement in that particular wave for voltage and I naught indicates maximum displacement for current. So why did we take the maximum displacements? That is because we need amplitude to represent a wave as a wave function. So we actually know that any wave can be represented as A, this is a sine wave, so A sine theta, or simply A sine omega t, and if there is a phase difference you can add the phase difference also. So this you have already studied in your PU first year. I'm not going to dive into it deeply. So anyways, so here this particular wave theta is obviously angular displacement, which can also be written in terms of angular velocity, that is omega times t, and phi is the phase difference. Here A is the amplitude. That amplitude is what we just found out, that is V naught, and in case of current it is I naught. And sine is the form of the function. Here it is like a sine wave, hence we took sine. We can also take cos if you want, but that'll be a little confusing. So again, sine is the function we choose, and omega t, that is omega will be the frequency of the wave, sorry, the angular frequency of the wave, and phi will be the phase difference, that is, if in this particular case, how much are they in phase? For example, V naught and I naught lie in the same line, which means the phase difference here is 0, which means both of them are lying in the same line. They are in phase with each other. They are constructively interfering. But if this wave moves away even a little, that is like this, then there is a phase difference of a certain angle that can be represented using phi. All these are basics you already know. I don't want to waste time reiterating that. So again, so the point here is that since we found out the maximum amplitude and we know how to represent a wave equation, we are going to write down this particular alternating current in terms of a wave equation. So we can actually represent current as I naught sine omega t and voltage as V naught sine omega t. Because again, the nature of the graph was very simple. If there is a graph, there will be a current and there will be a voltage. The only difference is that voltage was slightly higher, but both of them are in phase and they are like a sinusoidal wave. Hence, we can use a sinusoidal wave function to represent current and voltage. Now again, how do we apply Ohm's law? We know that V is equal to IR, or simply we can also say that V naught sine omega t is equal to I naught sine omega t R, or simply I naught into R sine omega t. If we consider the starting position, generally we can just write that V naught is equal to I naught R. This is generally the way we can actually represent Ohm's law in terms of alternating current, because we cannot actually take the average values and we cannot take a certain set of values because it is alternating, it is changing at every instant of time. Hence, we have to take the instantaneous values. So instead of taking the instantaneous value, we actually predicted the pattern of that particular wave and used a wave equation to represent that particular wave. Hence, we can actually represent the equation for Ohm's law as such. V naught is equal to I naught R, or simply V naught by I naught is equal to R. That is the general way of representing Ohm's law in terms of alternating current. And you have to remember that, always remember that in this particular equation, this V naught and I naught are the peak values. These are the peak values. So this is the highest value attainable by this particular wave. Hence, it is known as amplitude. Here it is the peak value I naught, and here it is the peak value V naught, which represents voltage and current. So this omega is nothing but, you all remember, omega is equal to 2 pi mu. That is a relation between angular frequency and linear frequency. I am telling you all this ahead because we have a lot of problems to be solved. This is a numerically important chapter. Theory wise, it's very less, but again, you have a lot of derivations and problems can be asked from this particular chapter. So you have to recollect all the information you learned in your first PUC. That is omega is equal to 2 pi mu, which is just a relation between angular terms and linear terms. So this is angular frequency, this is linear frequency, and 2 pi is just a constant relating them together. All the equations of Ohm's law and that is relating to current is actually applicable here also. The only difference is that we have to take the instantaneous values of current and voltage in order to apply them. That is the only difference, because alternating current is a phase differing current, or simply it alternates between its phases. So we have to be wary of that and understand and apply equations such. So we are going to actually find out what are the differences, what will be the nature of this particular current that we are using, and why we are using this particular current. We can just use DC current. Instead of that, we are actually connecting our wires through the KCB towards some dam or something which generates power, and it is using alternating current, which is producing alternating current that reaches our homes. So we actually know how this current is made because of last chapter's help, that is how we can generate power using a generator. Yes, how a generator generates AC power. Now we are dealing with how this AC power actually behaves. So first let's start from the basic. So if there was a DC circuit, let's say there was a DC circuit like this connected to a resistor, then we can actually say that it obeys Ohm's law and V is directly proportional to I, or V is equal to IR, and simply we can also say that the power of this particular circuit power is equal to I square R, or simply you can also say it as power can also be equal to VI. So this is all in the case of DC current. That is, if this is DC current, this is all true. Now, what do we do when it is AC current? That is, same circuit, there is a resistor, there is a power source which is an AC power source, and hence we have to apply Ohm's law. We just saw that we can use a generalized equation, V naught sine omega t is equal to I naught sine omega t into R, and we can also say generally V naught is equal to I naught into R, and we also have to find out what is the power. Here again the problem is we cannot take the average values. The average value is not takeable because it is not obtainable, because the average value will account to 0 because there is one positive half and one negative half to a wave. That is, if you are taking a wave, the problem is that if we take the average of this particular wave, one half is positive, one half is negative. Hence, average this plus this divided by 2 is actually 0. So we cannot take the average value. So what do we do? So what we can actually do is that we can actually take what is known as the RMS value. That is, we can actually take the RMS value. It is also known as root mean square value. So that anything that is coming negative, if we take the root of something which is negative, square it again, root mean square. So if there is any quantity inside which is squared of a root, it automatically comes out as positive. That's it. It is just a mechanism to convert this negative half into positive half so that we can take the average value. It is just a mathematical trick of getting the average value if any quantity is like this, that is negative and positive and negative and positive. We take the root mean square, hence it will come out as a positive value. Actually in the sense plus or minus x, but again we will only consider the positive value, hence we can use this trick to get the positive value. So before getting into all that, we know generally the equation for power is I square R or VI. I'm going to just take I square R here. So I square R is the equation. Here we know that I is equal to I naught sine omega t, and R is just resistor R. So we can simply say that power P will be equal to I naught sine omega t whole square. Remember, it is not I naught square sine omega t, it is I naught sine omega t whole square into R, or simply we can write it as I naught square sine square omega t into R. So this is the general equation we can actually represent to indicate instantaneous power. So power at any point can be given using this particular equation. I naught square sine square omega t into R. But again, we have to calculate the average power output. That is, what will be the average power given out by the AC current over a span of, let's say, this much time, or this much current given. How much will be the power output? So in order to calculate that, we cannot take the average value. And we saw that we can actually take the root mean square value. So what this actually does is that, what the root mean square value actually gives us is that, it will give an equivalent value that is similar to the DC output. Imagine that this circuit, that is the DC circuit, gives out 100 joules of heat. 100 joules of heat is given out by this particular circuit. So I know that this particular voltage, that is how much volt is coming into this system, what is the current, what is the value of resistance, all things I know. So I can actually say that, okay, this particular circuit is giving out 100 joules of heat. It is pushing out 100 joules of heat. So in order to calculate the same manner of power output in the AC circuit, I have to have a certain trick. This is the physical significance I'm saying. Mathematically, I just told you, we take the root mean square, which will be equivalent to the DC circuit. Physically, what it means is that this particular circuit, I know that this particular circuit current flows like a wave. It is like a sinusoidal wave. So I don't know the actual values, but I can adjust the values of instantaneous current and voltage. That is, I can control this output. That is, I can control the AC current, that is alternating current. I can control it so that this particular resistor also gets 100 joules of heat. So, in order to produce the same 100 joules of heat, how much power did I use? That particular relation will give you the equivalent values of both. That is, how much voltage did I use? How much current did I use in order to produce this 100 joules of heat? That can be equivalently related. That is what we are going to find out here. So RMS value will actually give the equivalent value of DC current. That is, if I say that I have IRMS, I am actually saying that this value of current is equal to the amount of current that will be flowing through a DC circuit under the same conditions. That is, if this DC circuit is producing 100 joules of heat, the equivalent current, that is I amount of current is producing 100 joules of heat, then the equivalent current that is used to produce the 100 joules of heat in this particular circuit will be the IRMS value, that is IRMS value. So basically, it's just a trick to get the average value where all the negative sides are pushed upwards so that you get an average value output. So we know that now power for an AC circuit is given by P is equal to, or power is equal to I square R, which can be written as P is equal to I naught square sine square omega t into R. Now, this is for just one point. We have to consider that alternating current is actually a wave. It is a wave function which travels throughout like this. So, if I take the time period to be t, that is in t time period or t amount of time, how much power will be consumed? So, we have to actually take the average power. That is the power at every point we have to take it and we have to find out what is the average power output. So, in order to calculate the average power output, we need to have the instantaneous values of current and resistances at each point so that we can get the average power output. So we know a trick for that too. Instead of summing individual points like this, we can actually integrate. So we can actually say that average power P bar, we can also indicate using brackets, but I'm just using P bar. So P bar is actually equal to, that is average power will actually be equal to integral, let's say 0 to t I naught square sine square omega t times R. This can again be simply written as integral 0 to t I naught square R sine square omega t. So again, the thing here is that this particular term, that is I naught R, this particular peak value, that is, if I take this particular peak value, that is the amplitude, it is not going to change, which means it is a constant quantity. And again, value of R, that is the value of resistor, it is also not going to change. It is also a fixed value, which means these two will act as fixed values, which means they can come right outside of the integral sign. Again, then we can actually say that this particular equation can be written as I naught square R into integral 0 to t sine square omega t dt. So integrating sine square omega t is very easy. You have the trigonometric identity, which is known as sine square omega t can be also written as cos 2 omega t. Yes. So sine square omega t can also be written as half into 1 minus cos 2 omega t. This particular equation can be rewritten as I naught square R into integral 0 to t half into 1 minus cos 2 omega t. So again, while integrating, you don't have to by heart all this. The only thing you have to know is the equation for power and the equation for average power. I just wanted to show you how this equation actually gives out the final form. Again, you don't have to by heart all this. While integrating, this cos 2 omega t term will actually account to 0, because integral cos will give you sine and 2 omega t, which means at every multiple, that is at every even multiples of sine will be 0. Hence, this entire term will vanish and only this one will be remaining. So, once we multiply this by half, the only thing remaining will be the half here. Hence, we can write it together. We will get the final form as I naught square R, which is outside of the bracket, and this half which is already existing there. So, we will get it as I naught square R divided by 2. That will be equal to the average power output. That is, so the only thing you have to understand from this particular equation is that power can be obtained using this particular equation and average power can be obtained using this particular equation. So I naught square R divided by 2. But the interesting fact is that since we took the RMS value, this I naught will be equal to IRMS. So this RMS value will actually have a certain interesting thing, that is, so the average power over the AC is given by I naught square divided by 2. That is the equation you are going to take throughout for the numerical problems if any comes. But again, the interesting thing is that when we compare it to a normal DC circuit, this I naught square by 2, that is, we have in the DC circuit, it is I square R, right? Here it is I naught square by 2, which means that I can actually say I is equal to I naught divided by root 2. That is, I square will be equal to I naught square divided by 2. This particular relation between the DC current and the AC current, that is given by IRMS is equal to I naught divided by root 2, is actually a very important thing you have to remember throughout this particular chapter. That is, the RMS value of current will be equivalent to I naught divided by root 2. And similarly, if we take for voltage, similarly we can also prove for voltage, but simply take my word for it. Similarly, for voltage also, VRMS will be equal to, that is, the average value of current, the average value of voltage will be equal to V naught divided by root 2. So this is how the RMS values are related. Remember, RMS value is just there so that we can equate AC current to DC current. So this is how the relation actually exists. So we know that IRMS is equal to I naught divided by root 2. VRMS is equal to V naught divided by root 2. Alternating current. So just to sum up everything and see if you have understood everything, let's take it back a notch. So if you get a question like this, how are you going to solve it? For example, the question is, an alternating current is given by the relation I is equal to 141.4 sine 314t. So the question is that find the peak value of current. Find the value of DC current which is producing the same amount of heat. That is basically meaning find the DC equivalent of this particular AC current. And then the next question is find the frequency and the time period, and finally find the instantaneous value of current at t is equal to 3 milliseconds. So how are you going to solve this particular equation? It's very simple. The first thing we have to do is that we have to write down what is given. So here it is given this particular relation. So the given quantity or given relation is that I is equal to 141.4 sine 314t, which resembles our equation I is equal to I naught sine omega t. So it is very clear that the first answer to this question, that is the peak value of current, is given right here. That is I naught is the peak value of current, hence I naught is nothing but the peak value of current is given by I naught. The peak value of current is 141.4 amperes. That is the peak value of the current. Now, the second question, find the DC equivalent of this particular AC current. Again, we have one simple relation, that is relating the RMS value. So the only thing we have to do is find the RMS value. This is for one. The second answer, that is the DC equivalent. So in order to find the DC equivalent, that is the RMS value of current, we also know that there is a simple relation, that is I naught divided by root 2. So dividing this particular equation, that is 141.4 divided by root 2, you will get the DC equivalent of this particular current. That is AC current will be converted into DC current. Always remember, taking the RMS value just means that you're converting AC current into DC current in these sort of problems. So in order to find out the RMS value, that is the DC equivalent, the only thing you have to do is write the equation, substitute the values. Now the third question, which is find the frequency and time period. That is also very easy because we know that omega is the angular frequency. Angular frequency is given by omega is equal to 2 pi mu. And we are asked to find what is the frequency, not angular frequency, what is frequency. So the only thing we have to do is that here identify omega, here it is 314. So you just have to find out what the natural frequency is. So natural frequency mu is equal to omega divided by 2 pi, or simply 314 divided by 2 pi, and you will get your frequency that will be given in hertz. And lastly but not leastly, we also have to find out what is the instantaneous value of current at t is equal to 3 milliseconds. So that is also very simple. Here t is given. The only thing you have to do is that substitute 3 there, that is 3 milliseconds. So 3 milliseconds is actually equal to 3 into 10 raised to 3 minus 3 seconds. So just substitute that value there and you will have the instantaneous value of current as well. So solving these problems is very easy. All you have to do is that identify the questions, understand what is being asked, and simply answer the questions. That is very simple. So I hope you have understood everything I have told you here today. What is AC current? What is the difference between AC and DC? How you can find out power? How you can derive various equations? What is the peak value? What is RMS value? What is I naught? What is V naught? So this is just an introductory class. We will get on with the real topics, what happens to AC currents when it passes through different circuits in the next class. Until then, I'll see you on. Thank you.